Welcome to the second lecture for nuclear forensics. This lecture is on the radiochemistry and nuclear forensics, and it's in 4 parts. This is part 1. The readings for this chapter is found in chapter 2, Physical Basis of Nuclear Forensics Analysis, in the Nuclear Forensics Analysis book. This lecture is going to cover the history of radiation research, and it's going to review materials of importance to nuclear forensics. The first lecture is going to cover nuclear properties, energetics, nuclear models, and decay modes. The following lectures will cover spin, parity, and decay, nuclear reactions, and nuclear fission processes. The final lecture will be a summary lecture that will highlight the material that will be of importance for the remainder of the course.
Radiation research can be traced back to the end of the previous century. In the 19th century, Dalton and the atom, Avogadro's principles, and Mendeleev and the periodic table set the groundwork for research in looking at the nucleus and nuclear properties. Röntgen discovered the cathode X-ray tube and X-rays from that in 1895. The year later, the discovery of radioactivity occurred with Becquerel and the Curies, as shown here, in which Becquerel used some uranium salts. He exposed it to sunlight, wrapped it in photographic plates that were wrapped in black paper. The plates revealed the image of the uranium crystals when developed. Becquerel incorrectly thought that it was basically a fluorescence or phosphorescence technique, whereas later showed to be that the photons were actually being emitted by the nuclei themselves. This result spurred a lot of other research. Isolation of radium and polonium by the Curies. This was isolated from uranium ore, and of course Marie Curie's famously associated with radium, and polonium was named after her country of birth, Poland. Right at the turn of the century in 1899, radiation was divided into alpha, beta, and gamma components based upon the ability to penetrate objects and cause ionization. Ernest Rutherford wound up identifying the alpha particle, showing it to be the helium nucleus around 1909. A number of other activities occurred before the discovery of nuclear fission. However, for this course, that's one of the obvious important dates in 1938 with Hahn, Meitner, and Strauss discovering fission. 1942, shown here, this is a painting of the Chicago pile. In December of 42, the first sustained human-controlled fission reactor by Enrico Fermi at the University of Chicago. This wound up being one of the genesis for the foundation of Argonne National Laboratory, where reactors were, as opposed to being built on the south side of Chicago, were then built in the south suburbs and then eventually moved to the Argonne West in Idaho. And then from this first nuclear reaction in 1942 came the ability to produce plutonium. The first fission bomb was tested in 1945.
One of the consequences of all this nuclear research that was ongoing was the impact on the periodic table. Today, here's an example of the periodic table. We see that we have up to 118 elements. And these include 2 of the most recently named elements, flerovium and livermorium. So prior to all this research on nuclear reactions, the periodic table really didn't have the actinides. Glenn Seaborg developed the actinide hypothesis and placed them below the lanthanides. And we also were missing a number of elements beyond uranium. One of the things that's germane to radiochemistry are the radio elements, and we see that there's 2 radio elements that are below bismuth, promethium here at Z of 61, and technetium here at 43. There's other radio elements. The elements polonium, actinium, radon listed here, the actinides here, and then some of the, just from francium on, and then the transactinide elements all the way up to element 118 where we currently stand today.
As part of this review, the decay modes and nuclear property should be discussed. Obviously the decay modes, alpha, beta, gamma, fission decays, spontaneous fission, and neutron-induced. Equations that are used for determining reactions, decay reactions. So one can use a standard equilibrium reaction. This is one drawn out in its entirety, where the number of the daughter atoms, everything for the daughter is represented by 2, is a function of the number of parent atoms, which are designated as 1. So this equation includes the decay constants for the parent and daughter and any original daughter that's present. One should also consider branching decays, which are just based upon the fact that your decay constant is a sum of all the decay constant modes. Usually one dominates, the other decay constants are insignificant. And the relationships can be drawn through the Bateman equation or programs which are used to relate parent and progeny decays. Another term that should be familiar is binding energy, or the difference between the constituent nucleons and the mass of the nucleus. This is often used to talk about nuclear stability, but it's also the conditions which drive fusion, where you can combine lighter nuclei into heavier nuclei, resulting in the release of energy, or fission, where you can take a heavy nucleus, split it into 2 lighter nuclei, and again, based upon the binding energy results. Also, with nuclear properties, one of the important components is the term mass excess, which is just the mass excess values are shown here, where you have the mass minus the A, and it's used to evaluate energies. One can take mass excess data in energy units for each nuclei that's involved in a reaction and use this to determine a reaction energy, such as the Q value, and the Q value is shown here. One can determine this by treating all the components of the reaction and solving for the mass differences. You can also you can do this directly for the masses and convert E equals mc squared, or just use the Q values. An example of Q value calculations are shown here. For example, just find the Q value for the beta decay of sodium 24. You can write the reaction, get the mass excesses this is from the mass values, convert that value from the masses with 931.5 MeV per AMU, and you can get a Q value. You can determine it straight from the mass excesses, same sort of value, slight differences. You can also use the Q value calculator, which is available at this site. There's also another Q value calculator, but this one is suitable for most calculations. And you can do the same Q value reaction for any sort of nuclear reaction. Here's an example for the electron capture of sodium 22. Again, we can determine it from the masses or the mass excesses, or you can insert 22 sodium and just and then insert a reaction, submit it, or just sodium 22 itself. If you just put in the isotope and put submit, a number of reactions will be provided. Another way of evaluating reactions is through the mass parabola, where the energy for a given isotope is shown, where at 0 energy is fundamentally a way of describing the stable isotopes. This is mass parabolas are useful for demonstrating stability for given mass chain. It also shows which mass chains may have multiple stable isotopes. For anything that's an odd A, as shown here with A of 75 or A of 157, there's only one beta stable nuclide, and it's near the minima in the parabola. So shown here, these are your stable isotopes. Right? We can see there's an energy difference here, energy difference here. For A isobars, there's possible to have 2 or even 3 beta stable isotopes, and these are generally conditions for even isotopes. This behavior is evident in the valley of stability, where if we took the chart of the nuclides, looked at the stable isotopes on one side, we would have isotopes one side of the valley of stability. We'd have isotopes that are beta positive unstable, and then we'd have other isotopes that are beta negative unstable. For nuclear forensics, understanding of nuclear models has an important role, particularly in terms of stability of nuclei and magic numbers. Some common components of nuclear models discuss levels and barriers that can be composed within the models. There's some differences between protons and neutrons. This has to do with Coulombic effects, that the proton has a charge and the neutron does not. So from some of the model developments, there will be different concepts related to potential and escape of particles from the wells in which they're in. And some of what's described here is really used for the basis of the shell model, where the shell model being an expansion from the liquid drop model, where there was failure within the liquid drop model to describe some trends that were observed around certain numbers. These were magic numbers. And also the shell model is useful for describing spin and parity, and can be used to assign spin and parity of nucleons, and how that relates to the overall spin and parity of the nucleus. And this was not something that was able to be performed with the liquid drop model. These concepts and ideas that we've just discussed can actually be applied to the shell model. And we've already kind of hinted at the shell model, where there's some experimental evidence. For instance, the ground state spin for all even nuclei is 0 plus. We've discussed magic numbers. So there are certain nuclei or certain states where there's enhanced stability for nuclei, which is pronounced in fission, for instance. There's some systematics on ground state spins for odd mass numbered nuclei, relationship between magnetic moments and their spins, and some of the properties of ground states of odd mass numbered nuclei can be determined from that odd unpaired nucleon. So it's as if I have an odd A nuclei, all the nucleons are paired except for one, and that one unpaired single particle provides the properties for the nucleus. That's fundamentally one of the bases of the shell model. One of the other things with the shell model that can be derived is stability of nuclei based upon the number of neutrons and protons. One of the bases of the square well is the potential in which the nucleons sit. A simpler model is to describe the nuclear potential as a square well. A little bit more advanced is the harmonic oscillator, where you get a parabolic shape of the potential. With the harmonic oscillator, we get energy levels that are regularly spaced, shown here. And this is useful really for only low-lying energy levels. If by changing the nuclear potential to a square well with rounded edges, as shown here, we enhance the stability of states near the edge of the nucleus, and we can take these, so we see a lowering of the energies, we see a splitting, and then this splitting goes even further when spin-orbit coupling is applied. And this allows us to see where the magic numbers come from, where we have gaps in the energies between the levels, and these occur at 2, 8, 20, 28, 50, 82, 126. So the shell model is really the square edges and spin-orbit coupling combined. the shell levels are filled based upon their relative energies, and we can define the states by two quantum numbers, n and l, n being a principal quantum number, l being angular momentum. And unlike electrons, nuclear states can have a 1p, a 1d, a 1f, a 1g. So there's a variation in behavior of the shell model with the electron model. What we can do, when we look at these states, we know that there are some states which are degenerate. So we can group some energy levels together. Degenerate states, if I take 2 times n plus l, those with the same numbers, so n and l, so 1s, the n would be 1, the l would be 0. Those states with the same 2n plus l are going to be degenerate, and they'll be grouped together. As an example, if we look at this state here, which is composed of the 2s and 1d state, 2s, 2 times 2 plus 0 is equal to 4, right? Because the n number is 2, the l number is 0 from s. Where d, a 1d state, the n is 1, the l is 2, where s, p, d, right? So 0, 1, 2, the d is 2. So that's 2 times 1 plus 2 is equal to 4. Those two states are degenerate. We can see the same thing shown here, where we have the 1g, 2d, 3s, where all these equal to 6, and those levels become degenerate. And then when we have spin-orbit coupling interactions, where we can split the angular momentum, where J equals L plus S. As an example for this, we could take the P states, where P is equal to 1. S can either be, the spin is either plus 1/2 or minus 1/2. So the splitting of the P states will either be a 3/2 or a 1/2 state. And this is split into a fourfold degenerate, for instance, in this case, a 1p 3/2, which is shown here, or a twofold degenerate 1p 1/2. And when we say a fourfold degenerate p 3/2, it means I can put 4 nucleons into that state. When I say a twofold degenerate 1/2, it means I can put 2 nucleons into that state. The other thing that we see is the gaps appear at the 1n quantum number. So see a 1s, a 1p, 1d, the gaps are here. 1f, the gap is here. 1g, the gap is between the two 1g orbitals that are formed. Same thing with the 1s, excuse me, the 1h. Even the 1i is at the lower, is at the gap that defines the shell, that defines magic numbers. And we see the 1j here defines the magic number of 184. So from these trends, from the quantum mechanics of the shells, we get a lot of properties that come out with the related to the shell model, particularly the magic numbers and how many nucleons can go into the different orbitals. So the nucleons fill the shells in the shell model from lowest to highest energy. And as we already discussed, an odd A nucleus with one unpaired nucleon will provide the property of the nucleus. It'll basically have some sort of even-even core with one unpaired nucleon. So whatever state that unpaired nucleon is, the spin of that state will define the spin of the nucleus. The parity will be based upon the orbital angular momentum. So S's, D's, G's, I's have even parity. P's, F's, H's have odd parities. For odd-odd nuclei, where one odd proton and one odd neutron each contribute to the spin and parity, there's no universal rule, and we'll provide some examples of how you can estimate the spin and parity of odd-odd nuclei. Here's our shell model, and here's some of the properties that come out from the shell model. The lowest level is obviously this 1s. It's a s1 half. Since L is 0, J is only equal to the L plus the S, so 0 plus 1 half. It only has the one value. It's shown here, and it contains two nucleons. So I can put two nucleons into the shell. For the proton side, I can put two protons. For the neutron side, I put two neutrons. These are the total number, and that's a magic number. So for the shell model, there's a component that is for the neutrons and a component that's for the protons. The next level, we get to the 1p orbital, which splits into the 3 halves and the 1 half, and that's shown here. And we see that for the lower lying 3 half state, we can put 4 nucleons in. The total amount of nucleons will be 6, so this will be either the 6 protons or 6 neutrons completely filling this shell. The P1 half, I can put 2 nucleons, total number of 8, and this is a gap where 8 winds up being a magic number. So something where I have 8 protons and 8 neutrons, which would describe oxygen 16, should be especially stable from the nuclear component. We see the other shell closures at 20, 28, 50, 82, 126, and then 184. These enhanced abilities from the magic numbers correlate with these gaps in the shells. A few stable nuclei have both closed neutron and proton shells. They're very strongly bound relative to their neighbors. We can also call these doubly magic nuclei, and some examples are listed here. Helium 4, oxygen 16, calcium 40 and 48, lead 208. We can also find doubly closed, doubly magic nuclei that are unstable. Examples are given here, and particularly tin 132 being one of the driving force in the asymmetric fission distribution. So the other aspect of the shell model is here where we can see the number of nucleons, either neutrons or protons, that can fill a given shell, the total amount of nucleons at that given point that fill the shell, and then finally the magic numbers. So as an example, if I have a nucleus with 21 protons and an even number of, say, 20 neutrons, the 21st proton is unpaired. So that'll be, I can put 20 here. The 21st will go into this 1f 7 halves level. So the property of the nucleus will be dictated by that unpaired nucleon in this level. We'll go over some examples. Let's consider lithium 7. 3 protons, 4 neutrons. The proton number is odd, so that's the odd proton is going to define the behavior of the nucleus. And we see that this one unpaired proton, the third proton, lives in this 1p 3/2 level, right? Because I can put two protons here, the third one is here. So the spin and parity are based upon this unpaired proton. The spin, if it's 1p 3/2, the spin should be 3/2. The parity is based upon the p state. It has an L value of 1, so the parity, that's odd, so the parity is negative. And as we see, lithium-7 is 3/2 minus, as predicted from the shell model. We see here, this is the state that it occupies, and the 1p 3/2 correlates to 3/2 minus ground state. The excited state, shown here of lithium-7, is 1/2 minus. So the question is, if I have an excited state, I can either take the unpaired proton and excite it, or split one of the paired neutrons and excite one of those. It's much easier for the first excited state just to take the unpaired nucleon and excite it. So the unpaired nucleon would be living in this 1p 3/2. The next state up would be the 1p 1/2 state. We would expect the excited state of lithium-7 to have a spin and parity based upon the 1p 1/2. So the spin would be 1/2. The parity based upon the angular momentum p. It's an odd L, so it should be negative parity. We would predict that it would be 1/2 minus, and that is what we see. The excited state's 1/2 minus, and it correlates with the shell model. We can now consider an example that's a little bit more complex than lithium-7. Let's consider nickel-57, which has 28 protons, 29 neutrons. So that odd 29th neutron, that's going to define the behavior of the nucleus. 28, 29th, that lives in the 2p 3/2 orbital. p 3/2, p has an angular momentum of 1, so negative parity 3/2. We would expect the spin and parity of nickel-57 to be 3/2 minus, and sure enough, the ground state is. So let's consider the excited state. The excited state is 7/2 minus, and if we look here, the 29th neutron is here. If we excite that, we go to a 1f 5/2 level, which is what we see here. So F being negative, 5/2 state. So this also seems to correlate with nickel-57, 28 protons, by the way, magic number. So the nickel-57 is fundamentally one off from being a double magic nucleus. Another example, carbon-13, that's 12 protons, 6 protons, 7 neutron. The 7th neutron is unpaired. That 7th neutron, 6 will fill up here. 7th lives in the 1p 1/2 state. P, as we've already seen in the examples, is a negative parity, 1/2. We would expect the spin and parity of carbon-13 to be 1/2 minus, and it's true. Another example is with vanadium-51. The odd nucleon is the 23rd proton. 20 protons fit into this 1d 3/2, so I can put 3 into the 1f 7/2. 1 is unpaired, so F is also negative, so we would expect vanadium-51 to have a spin and parity of 7/2 minus. Now the shell model isn't always correct, and as an example, let's consider barium-137. the 81st neutron is unpaired in barium-137. That would leave a hole, right, almost completely filled 82 nucleons. So 81 is the 1H11 half state. That would be 11 halves minus. And if you look at the table of the isotopes for barium-137, you see that it is actually 3 halves plus. Now there are some rules with this. Generally speaking, high spin states generally do not appear as ground states. So it's relatively rare to see something like an 11 halves minus as the ground state. And also the shell model is based upon a spherical nucleus. If the nucleus is not spherical, then the shell model will not actually predict the state. We'll discuss this in some later slides when we discuss the Nielsen diagrams. We've shown examples of determining the spin and parity for nuclei with one unpaired nucleon. We didn't go over with even nuclei because those are 0 plus for the ground state. Now if we have a condition where we have an odd number of protons and an odd number of neutrons, so the spin and parity of the nuclei is determined by the coupling of each unpaired nucleon. One thing that we will see from a trend is that the spin values are integer values. And if we think about if we add two half integer values together, we should get a whole number. So we're going to get these integer spin values. Sometimes the coupling method isn't completely straightforward. One route to determine this is the use of the Nordheim number, where the Nordheim number is the sum of the spin and the orbital angular momentums. If we add the numbers together and the Nordheim number is even, then the spin is the difference between the two numbers, the absolute value of the difference. If the Nordheim number is n, we have two numbers that are possible, either the absolute value of the sum or the absolute value of the difference of the spins of the two states that are occupied by the unpaired nucleons. The parity is from the sum of the angular momentum states, the L states. If that sum is even, it's positive parity, and if it's odd, it's negative parity. We'll go over some examples to show how the Nordheim number works. For an example of the Nordheim number for an odd-odd nucleus, let's consider chlorine-38. Chlorine-38 has 17 protons, 21 neutrons. 17th proton is going to live in this D1D 3/2 state. So the L is D, right? So D is 2, S being 0, P being 1, D being 2. And J, the spin, is 3/2. The 21st neutron, there's 20, 21, is here in the 1F 7/2 state. So L is 3 for the F state, J is 7/2. So the Nordheim number is just 2 plus 2 plus 3/2 plus 3 plus 7/2. That's equal to 10. That's an even number, so the spin is just going to be the absolute value of the difference between 7/2 and 3/2. 7/2 minus 3/2 is 4/2. The spin is 2. The parity is from the L's. So that's 3 and 2. The L is 5, negative parity. The spin is 2. The parity is minus. We expect chlorine-38 to have a spin and parity of 2 minus. If we consider another example of aluminum-26, this is a nucleus with 13 protons and 13 neutrons. So this 1D 5/2 would be filled to 14, so there's a hole, there's one less, there's one missing spot for each the proton and neutron shell. So each particle, unpaired particle, has the spin of 5/2 and an orbital angular momentum of d of 2. So the Nordheim number is 5/2 plus 5/2 plus 2 plus 2. That's equal to 9. That's an odd value. So the spin is going to be the absolute value of the sum or the difference of the spin values. Each spin value is 5/2. So 5/2 plus 5/2 is 5. 5/2 minus 5/2 is 0. We would expect the spin to be either 5 or 0. The parity, each spin state is 2. 2 plus 2 is 4, is even. So the spin's either going to be 0 plus or 5 plus, and the actual value is 5 plus. So here's an example with the odd Nordheim number where you get a choice of answers to evaluate. And here's an example of that fine structure as we discussed with alpha decay. So you see here, here's an example of a alpha decay spectrum that one could take for the decay of thorium-228. We see that there's a few different alpha decay energies observed. And I want to point out that this is log counts versus channel number. The channel number is directly correlated with energy. So we see that there is one peak that dominates, but a few peaks that can be observed at relatively low intensities. This relates to the decay scheme where the bulk of the thorium-228 decays to the ground state of the radium-224. There are certain transitions that decay to higher level states of the daughter. There'll be less alpha energy, and they're accompanied by gamma decay, and that sum of the gamma and the alpha equals that entire energy drop. So the alpha decay energies can vary for the same isotope, and we know that when we look at the chart of the nuclides, we have different alpha decay energies listed for a given isotope. There are over 350 alpha-emitting nuclei, and as I showed here, these alpha decay energies can be used to develop decay schemes. Fundamentally, all nuclei that are greater than 150 mass are thermodynamically unstable against alpha emission. That means they have a positive Q value. However, the probability of some of those decays are rather small compared to competition from beta, so you generally see alpha with isotopes that are greater than 210. This isn't completely true. As we see here, their energy ranges from about 2 MeV to almost 12 MeV, where neodymium-144 is a very low energy alpha emitter in the lanthanides, and polonium-212 metastable is a very high energy. We're also going to see a correlation between half-life and decay energy, where the neodymium half-life is almost 10 to the 30th times longer than the polonium-212. And what we're going to find out is that, generally speaking, the shorter the half-life, the higher the alpha decay energy. There are some trends that can be observed with the Q value energetics for alpha decay. One is that the Q value generally increases with A. So if we look at all the isotopes together and we increase A, we see that there's a general trend that as A goes up, the Q value increases. However, this is not generally true for a given isotope. If I look at a given isotope, for instance the lead here or the bismuth here, plutonium here, as I increase the A for a given isotope, the Q value generally decreases. There's also some shell effects that we see with this Q value. We see peaks at N of 126. We also see that there's alpha decay near the 82 neutron closed shell, which is found in the lanthanides. We get an increase in the Q value there since we get an increase in the alpha decay energy. The alpha half-life decreases so that we can start to see some competition between alpha decay and other modes of decay. There's also some short-lived alpha emitters near doubly magic tin 100, and you can examine this on the chart of the nuclides. Look at some of the isotopes that are listed here. And alpha emitters have also been identified by the proton drip line above A of 100. And the proton drip line is that part of the chart of the nuclides, which is right at the very edge, the left-hand edge, so the very, very light isotopes of the elements. And A above 100, if you inspect that area of the chart of the nuclides, you'll see some alpha emitters.
the alpha decay energetics allows us to calculate the Q value and the alpha decay energy for a given isotope. We know that the Q value often exceeds the alpha decay energy, and this is due to the fact that the Q value is the total energy of the system, so it's the kinetic energy of both the alpha particle and the daughter. We have a relationship where the momenta are going to be equal in opposite directions for the kinetic energy, for the daughter and the alpha particle, so we can use this equation where mass times kinetic energy for the alpha is equal to mass times the kinetic energy of the daughter. We can rearrange this equation and we can solve for the kinetic energy of the daughter as a function of the mass of the alpha, the kinetic energy of the alpha, and the mass of the daughter. We can substitute this into the Q value equation, and we get a relationship in which we have terms of the kinetic energy of the alpha, mass of the alpha, and the daughter. We can rearrange this. This is shown here, and we end up with a final relationship where we can say that the kinetic energy of the alpha particle is equal to the Q value times the mass of the daughter divided by the mass of the alpha particle plus the mass of the daughter. From this equation, we see that the bulk of the kinetic energy value is taken up by the alpha particle. So the Q value is often close to the alpha decay energy. From the semi-empirical mass equation from alpha decay, we know that an emission of an alpha particle lowers the Coulomb energy of a nucleus. This increases the stability of heavy nuclei while not affecting the overall binding energy per nucleon because an alpha particle is emitted, and if you remember from the figure of the binding energy versus alpha particles have very high binding energies. So we can use the calculations that we discussed to evaluate Q values for reactions. So as an example here, if we wanted to evaluate the Q value of the decay of uranium-238 to thorium-234 plus an alpha, if we get the mass excesses of uranium-238, thorium-234, and an alpha particle, we can arrange this equation. We can see that the Q value is 4.27 MeV. Then we can use this to plug into our equation here and calculate what the Q value, from the Q value, what is the alpha decay energy. We see that the Q value is 4.27 and our alpha decay energy is 4.198 MeV. One interesting observation about these energetics is that the alpha particle energy is often less, and often far less, than the Coulomb barrier of the alpha particle and the daughter. So in other words, the energy that it takes for an alpha particle to leave the nucleus is often much, much less than the energy needed to push that alpha particle into the daughter to reform the nucleus. And we can evaluate this by evaluating the Coulomb barrier. And here's our equation that we'll use for the Coulomb barrier. 2, because since we're using this solve for alpha, the Z of the alpha particle is 2. 2ZR 1.44 MeV. So we'll rearrange this equation, plug in the values for the particle that we're interested in. So let's look at this for uranium-238. The alpha particle Z is 2. For 238, the daughter would be thorium, so we use a Z of 90. We put in the values 1.2 times A daughter to the 1/3 plus helium nucleus to the 1/3 times 1.44 MeV Fermi. And what we get is a Coulomb barrier of 28 MeV. So this says the alpha decay energy, while it emits with on the order of 4 MeV, to reverse the reaction would take 28 MeV. So the alpha decay energies are small compared to the energy required for the reverse reaction. So this is an idea that can be used to figure out how does this mechanism occur and how does the alpha particle leave the nucleus. As we discussed earlier, alpha particle emission can often demonstrate fine structure. And this is due to the fact that the alpha particle during the decay, the parent can decay to an excited state of the daughter. And this is often due to the fact that the daughter nucleus and the parent nucleus spin and parity need to match up to a certain degree. So for instance, californium-249, it goes to the 9th excited state of curium-245 because that is the lowest lying state with the same parent spin and energy. So, and we'll discuss this in a little bit more detail so that we can understand why certain isotopes have fine structure and certain don't. For instance, even nuclei, since their spin and parity is 0 plus, will often decay to the ground state of the daughter because their spin and parity is 0 plus, and the alpha particle also has 0 plus spin and parity. We can also observe something called long-range alpha decay, which is really the decay from a metastable state to a ground state of the daughter. So for instance, polonium-212, that sits almost 3 MeV above the polonium-212M. It sits about 3 keV above the polonium-212 ground state. And it decays to lead-208 directly with an alpha particle of about 11.5 MeV. And what's interesting about lead-208 is the magic nuclear properties of lead-208 can help drive that ground state, that decay from the metastable state all the way to the ground state of the daughter. There are some systematics that can be observed from alpha decays. We've already discussed the Coulomb potential has a way of accelerating the higher mass products out of the nucleus. And with a larger mass that's often observed, so larger A's that decay, the daughter and alpha particle can start further apart within the nucleus. So that's another reason that this potential exists, so that alpha decay occurs with higher A nuclei. One of the things that we can observe through alpha decay is some effects of the mass parabola from semi-empirical mass equations. And this example is shown here, where we can get alpha decay occurring and with accompanied beta decay. So as we see, as an example here, we get a decay from a higher state through alpha, and we can observe beta decay because once the isotope is on this mass parabola, it can go to the lowest state. The other thing we observe is we get areas where we can get branch decays, so where there's probability of either a decay through beta or a decay through alpha. So this is why we can get branched decays within the decay chains for uranium and thorium. Now, everything we discussed related to the model really holds for even nuclei. If we have odd, even odd, or odd, even nuclei, the half-lives are even longer than predicted due to something we're going to call hindrance factors. Now, the model assumes the existence of preformed alpha particles in the nucleus. And the ground state transitions from nuclei containing odd nucleon can only take part if that odd nucleon becomes part of this emitted alpha particle. So if I think about it, if I have an odd nucleon, that means that the highest energy nucleon in that nucleus is unpaired. In order for that to become part of the alpha particle that's emitted, a nucleon pair has to be broken. So this is a pretty unfavorable situation because the alpha particles can already be formed from existing even pairs. So this gives rise to this observed hindrance. And the alpha particle needs to be composed of existing pairs in such a nucleus. The product nuclei is going to be in a higher state. This can also explain why there's a high probability of transitions to excited states in the daughter nuclei. Now, the hindrance factors have been evaluated, and they're generally between 1 and 3 times 10 to the 4th. There's 2 ways of evaluating the hindrance factors. They're listed here. One, we can make a ratio of the measured alpha decay half-life or the calculated alpha decay half-life. Or the converse of that is I can do a ratio of calculated alpha decay constants over measured alpha decay constants. Either way, I'll get the same hindrance factor. This is because, well, there's a relationship between the decay constant and the half-life, or log 2 divided by the half-life is equal to the decay constant. But this is an important equation to remember, and use this to determine the hindrance factors. And it doesn't matter if I take the ratio of the alpha decays or the ratio of the decay constants. What you should remember is that the values are going to be greater than 1. So if you use an equation and you make a calculation and the hindrance factor is below 1, chances are all you need to do is take the inverse of that. Now, why we can calculate these hindrance factors, they're actually available in the table of the isotopes. As an example, let's look at the transition of americium-241 to the neptunium-237 via alpha decay. Here's the data in the chart of the nuclides. We get the half-life of the americium-241, its spin and parity, the Q value, and then a bunch of these numbers that are listed here. And these are our hindrance factors. So states of neptunium-237 that are in the 5/2 plus ground state and 7/2 plus the first excited state have hindrance factors of about 500, and you can see those values listed right over here. So we can say that this isn't a particularly favored transition. However, the americium-241 sits in a 5/2 minus state right there, and if we see that there's a 5/2 minus state right here, the main transitions go from that 5/2 minus state in the parent to the 5/2 minus state in the daughter. And these are practically unhindered transitions. We see the hindrance factor is just barely over 1. And the reason for that has to do with the similarities between the spin and parity states of the parent and the daughter. The spin's the same, the parity is the same, so there's no hindrance. We see that the ground state, the spin is the same, but there has to be a parity flip, so that's going to increase the hindrance. As we can see, the values can go anywhere from 1 for a hindrance factor to thousands. And as we see again, this relationship is driven, this spin and parity state from the parent to the daughter being the same is manifest by a low hindrance factor. So we should be able to evaluate something about changes in spin and parity as it relates to hindrance factors. And this is exactly what we see, is that there's 5 classes of hindrance factor that are based upon some values. And we can describe the transitions as favored or less favored. If you have a hindrance factor between 1 and 4, the transition is a favored transition. So the emitted alpha particle is from 2 low-lying pairs of nucleons. Hindrance factors between 4 and 10 indicate a mixing or favorable overlap between initial and final nuclear states. 10 and 100 usually means that the spins of the initial and final states are going to be the same, but the wave function overlap is not favorable. Higher factors indicate that a change in parity is going to occur, but with projections of the initial and final state being parallel, and hindrance factors of 1,000 or greater indicate that the transition involves a parity change and a spin flip. So the more fundamentally from this information, hindrance factors go up when changes from the parent to the daughter become more involved in terms of having to change spin or having to change parity.
This completes the first part of Lecture 2 for nuclear forensics, radiochemistry, and nuclear forensics. Please, when you've completed this part, continue with Part 2, where we'll discuss more decay modes and spin and parity and how it relates to decay.